great news today is that you kind of already know how to do what we're going to do. Today is to find the area bounded between two curves. So far we found area bounded beneath the x-axis. And what we've learned about area is that you need to find the width and you need to find the height. So I'm going to begin to describing this just a little bit different than we had before, but I'm going to draw one rectangle here. And when we find area of rectangles, we don't like to do just one rectangle. How many rectangles do we like to do? We like to do an infinite number of rectangles. And that's the awesome thing about calculus is in order to move to an infinite number of rectangles, all you have to do is just slap on this integral thing. And we move from 5 rectangles to an infinite number. Yep. And so we talk about the width of each rectangle. The width moves from, say, I don't know, a half a unit or a tenth of a unit. What eventually does the width become? Moves all the way towards like 0, doesn't it? It gets smaller and smaller and smaller. So we call the width of a rectangle, we call it dx. And we call it dx because it has horizontal width. If it had vertical width, we would call it dy. Right now we're going to focus on dx. Suppose that f of x had a height of, I don't know, we'll say 10 right there. And suppose it had a height of, we'll say 4 right there. Does anybody tell me what would be the height of the first rectangle? 6. You took the height at f of x and you subtracted the height at g of x, correct? So therefore, the area of one rectangle becomes the width, which is dx, times the height, which is f of x, minus g of x. That's how we find the width of one rectangle and the height of one rectangle. That gives us the area. Instead of doing the area of one rectangle, we want the area of an infinite number of rectangles. So we slap on the integral symbol. We go from a to b. And we do f of x minus g of x dx. It's important to note that f of x is the top function and g of x is the bottom function. Top and bottom. Okay. Pretty straightforward, isn't it? You're going to like it because the example works out quite well for you. It says, find the area bounded between y equals x squared and y equals negative 2x plus 3. And we're not going to look over a certain interval. We're just going to find the area in its totality. I'm going to change that slightly. And we're going to start by sketching a graph. So again, I just want to remind you guys something to keep in mind. So here we have it. I'm going to graph this region so I can understand what it looks like. What does the graph of x squared look like? A parabola. And then I have the graph of negative 2x plus 3. What does that look like? Line that shifted up 3 units has a slope of negative 2. I would like to find the area bounded between those two functions. So as I draw a rectangle between those two, if you look at the width of the rectangle, it has what we call horizontal width. So I classify it as dx. If I want to determine the height of the rectangle, I do the top function minus the bottom function. What's the top function? I'm not giving you guys the whole picture. Tomorrow we're going to look at rectangles that are drawn sideways. And then that would have dy, would have vertical width. So, and it's no big deal. You'll do fine with it. But right now we have horizontal width. That's going to become very critical tomorrow as we move forward. Which one's the top function? Yeah, negative 2x plus 3. I take that and I subtract the bottom function. What's the bottom function? X squared. So you could draw any rectangle you want to, and that would always be the case, right? No matter where I draw it, the line's on top and the parabol's on bottom, correct? So therefore, the area of one rectangle is the width, which is dx, times the height. The height is the top minus the bottom. So I'm going to write that negative x squared, positive 2x or negative 2x? Negative 2x plus 3. That's the area of one rectangle. How many rectangles do I want? Infinite. No problem. We just do that. What am I missing? The bounds of integration. So I need to decide where I start and where I stop. Everybody agree that I start there for some x value and I stop there for some x value? I wish I could figure those spots out. That's where they intersect, and Ishika and Riker say set them equal to each other and find where they intersect. We can do that. We're wondering where is x squared equal to negative 2x plus 3? How do I solve that? Get everything on one side. X squared plus 2x minus 3 is equal to 0. Factor, and I get x minus or plus 3, x minus 1. So the solutions are negative 3 and positive 1. So I have negative 3 and I have positive 1. Those are now my bounds of integration. Let's determine the antiderivative. What's the antiderivative of negative x squared? Over 3 minus x squared plus 3x evaluated at 1 and negative 3. What do you get? 1. Negative 1/3 minus 1 plus 3 minus, now I plug in negative 3. Negative 3 cubed. Negative 27 times a negative positive 27 divided by 3. 9. Minus plus. Look at that. It's just like, yay, we're straight up that. I find common denominators. Negative 1/3 plus 33/3 is 33. 32/3. What do you think? Not too bad? So, you know where people struggle with this unit then? Generating the picture. So do you know what the graph looks like? I want you to notice my bounds. I came up with -3 and 1. Does it look like -3 and 1 would be reasonable bounds? Yeah. And then the top minus the bottom, just knowing which one is on top, which one is on bottom. I assumed when I started teaching for many, many years that the graphical piece just came naturally to everybody. That's not the case. And so get used to kind of graphing them. I can't simply plug in two functions in my calculator and find the area between them. Your calculator doesn't do that, so it's much more difficult to actually check your answer. What do I love about this? You have which antiderivative. We try one more. Find the area bounded between the curve y equals x squared. Actually, you know what? That is our interval. So we don't have to determine the bounds of integration. Do you know what the graph of sine of x looks like? Tell me. How do I divide it up into 4 parts? Starts at from 0 to pi over 4. Hopefully, the cosine graph is on top the entire time. And this is what we're doing in college trig right now. There's a little bit of panicking happening. Anybody know how I solved that equation? Divide by cosine, and you get tangent of x is equal to 1. Great. Where is tangent 1? Or when is the x coordinate the same as the y coordinate on the terminal point? 45 degrees. Very good. Root of 2 over 2. So that would be our angle, root of 2 over 2. antiderivative of negative sine plus cosine of x. Yeah. Minus, now I plug in, and I get sine of 0 is 0, and the cosine of 0 is 1. So what is the root of 2 over 2 plus the root of 2 over 2? 2 roots of 2 over 2, which is the root of 2. And then 0 plus 1 is 1. And so between 0 and pi over 4 is exactly root of 2 minus 1. Yeah. Good work, everybody.